Hi, this is Chris with Sanderson Test Prep, and in this video we are going to take a look at one of the most classic related rates questions that you'll see, and that's the falling ladder question. So let's take a look at this problem that we see here. A 10-foot ladder is leaning against a house on flat ground, and the base of the ladder starts to slide away from the house. The base is moving horizontally at 2 feet per second. How fast is the top of the ladder sliding down the wall when the base is 8 feet from the house? Okay, so first we want to try to draw a figure so that we can understand the scenario being described. So here we'll do our best attempt at drawing a house. So a couple windows, a door, and a roof. House. Okay, that's the best we can do. Then we're going to have our ladder leaning against the wall of that house and the flat ground that the ladder is on. So this is the scenario that they're describing in this question here. Let's see what we can label. So it says it's a 10-foot ladder, so let's go ahead and label that as 10. And it says that it's sliding away from the house, which means that it's going to be sliding in this direction. And the units they give us here are 2 feet per second. So it's a 10-foot ladder, and then the base is moving 2 feet per second away from the house. Okay, and they want to know how fast the top of the ladder is sliding down, right? So the top's going to be sliding down. That's what they're asking about here. When the base is 8 feet from the house. So this will be 8 feet at that time. Okay, so we have all the information from the question. So now we really just need to work with our figure. And let's look at this. I'm going to just redraw this in more simplistic form as a triangle, but sometimes it is helpful to draw the actual scenario so that we can even figure out what shape we're dealing with. But here, if we ignore our house, so we're going to get rid of that beautiful artwork, and we're just going to simplify a little bit. This is just a triangle. It's a right triangle, and we're going to take a look at some of the values that relate the sides of this triangle to each other. So for simplicity's sake, a lot of times with a triangle, we might be used to using A, B, and C so that you can do Pythagorean theorem with A squared, B squared, and C squared. And that can certainly work. However, I think that in keeping track of which side is which, it's a little bit easier when dealing with related rates to use those other sides as your x's and y's when you have a horizontal and vertical component to the question. So let's look at this one as x and y, and then we can still call our hypotenuse on this c if we'd like to. So if we look at this question with Pythagorean theorem, we would have an x squared plus a y squared equals a c squared. So that's what Pythagorean theorem would look like for this question. But as we know, with related rates, we're going to be taking a derivative of our primary equation, and we're going to try to find, if possible, some relationship among these variables. And we also have to figure out which parts are the variables themselves, and then which parts are going to be the rate of change, or the derivative of those variables. So first, let's write out the derivative of this equation using what we know from implicit differentiation. So here, our derivative, this will be 2x, and everything here is going to be over time for these rate of changes. It's feet per second, right? So this is going to be 2x and then dx dt. So that's your change in x over your change in time. That's showing that it's a rate of change. And we're going to do the same thing here, 2y, and then times dy dt. And we're going to do the same thing here, 2c times dc dt. All right, so now we have our derivative. And let's take a look and see what we can plug in and then what's missing and what we're going to have to solve for to add to it. So remember, the question itself, I'm going to put this in red, but the question is asking about this rate of change on the y-axis, which means that is your dy dt. So we won't have anything that we can plug in for dy dt. That's going to remain a variable. But let's plug in the other information that we have. And let's see what we've got here. So here, our x value we know at the point in question is going to be 8. Our dx dt, that's our change in x. That's that rate of change of the base of the ladder that's sliding away from the house. So that's going to be times 2 plus 2. Now we should have something here for y. We don't have it yet, but let's see if we could figure it out at this point. If our hypotenuse is 10 and our base is 8, can we find the value of y? We know we can't find dy dt, that's what we're going to solve for, but can we find y by itself? In this case, we can. If we're really savvy, and hopefully, by the time we're in calc, we've really internalized those different kinds of Pythagorean triplets. But this is an expansion of a 3, 4, 5 right triangle. This is a 6, 8, 10. So our value of y here would be 6. If we didn't know it, you could solve for it using Pythagorean theorem. So you could plug it back into this original equation here, and you could say, okay, well that would be 8 squared plus y squared equals 10 squared. And you'd have 100 minus 64, which is 36, square root of that gives us 6. So you can always solve for it if you need to, or if you have numbers that aren't as friendly, but in this case with a Pythagorean triplet, we really should aim to recognize that. And then the dy dt, as we said, that's going to remain as our unknown. Now let's take a look. 2c. C is 10. And then here's where a lot of people get stuck on this question. They say, I don't know a value for dc dt. And we don't have a labeled value for it, but we do know a value because dc dt means the change in the hypotenuse over time. And as our ladder slides down the wall, is the ladder stretching or is the ladder shrinking? No, the ladder is staying the same length. The ladder is one object. Its orientation is moving around, but the ladder itself does not change in length. So the dc dt on these falling ladder questions, the actual ladder itself has no change over time, which means that value is going to be 0. And we actually like that. It's going to simplify our math quite a bit. But a lot of people get stuck there and don't know what to plug in for the dc dt. And then once we do that, here we can go ahead and just numerically solve. So 2 times 8 is 16 times 2 is 32 plus 12 times dy dt equals 0. We subtract the 32. 12 dy dt equals negative 32, and we divide by 12, and we'll get negative 32 over 12, which if you divide them both by 4, simplifies to negative 8/3. And the units will be the same as they are on the x. That's going to be in feet per second. So that ladder is sliding down the wall at about 2 2/3 feet each second. So that's how fast that top of the ladder is dropping down the wall in this falling ladder question. If you have more related rates questions, check out our other videos, and thanks for watching.